as we look at the general properties and structure of our alkynes, it's immediately apparent that we have a lot of similarities to our alkenes. Right? So they both share pi bonds between carbons. They both tend to be somewhat nucleophilic due to the high electron density and those pi bonds between our two carbons. So it should be no surprise then that our alkynes use a lot of similar reactions to our alkenes. As we've said, we'll have kind of the same addition reaction, but then we'll be able to extend it just kind of one step further because of our additional pi bond that we have in our alkynes as compared to our alkenes. So today we're going to be looking at our alkyne addition reactions, and we'll be seeing how they are very similar to their alkene counterparts, but then how we can extend those due to our extra pi bond. We'll start with our hydrogenation. Now in a hydrogenation, we're using hydrogen gas, right? So we're going to be adding hydrogens onto both sides of our carbons, right? We're using the electrons to attack and add on these hydrogens. We're always reacting with a metal catalyst. Nickel, platinum, palladium are commonly used. Right? Our hydrogens will be attached to this metal surface, and our alkyne will come in and pick up those hydrogens. So of course, if we add two hydrogens onto our structure here, we would expect that we'd go from our alkyne to our alkene. Right? So that would be with two additional hydrogens. Again, as always, our R's are just representing any general carbon-based chain, or it could even be hydrogens. So that would be our acetylene in that case. So we get our alkene product, and it might be tempting to say that this should be the end of our hydrogenation. But unfortunately, our alkene, of course, is also reactive under the same conditions. So if we have that hydrogen gas present and our metal catalyst, we'll react our alkyne to our alkene, but our alkene will actually continue to react. It will react again, and we'll go to our alkane. So this might be fine if we want to produce an alkane, but it can be problematic if you're looking to create an alkene from your alkyne. So again, we add on our two hydrogens, but we go one step further and add on hydrogens to our second bond. Right, so we're adding it to our first pi bond and to our second pi bond to produce our final alkane. So we can start with some initial alkyne, like our butane here. And if we react it with hydrogen and I'll say platinum, we would produce butane. So what if we want to stop with our alkene product instead of continuing all the way to the alkane? Now of course, in this case, we need to figure out how to slow down our reaction, right? Because normally it reacts too quickly all the way to our alkane, and we can never isolate that alkene. Our catalyst is key towards speeding up this reaction. So if we want to stop with the alkene, we need to do something with our catalyst such that it reacts more slowly, and we can isolate just that alkene product. So what we're going to do is we're actually going to poison our catalyst. And what I mean by this is we're just going to modify it so that our reaction rate is slower so that we can produce our alkene. The particular catalyst that we use for this is called Lindlar. Particularly we use Lindlar modified palladium. So Lindlar is just the name of the scientist that discovered this particular catalyst. This catalyst will slow down our reaction and allow us to end at the alkene. So our reaction then would look like this. We have our starting alkyne, and we're reacting it again with hydrogen. And on the bottom for our catalyst, we're just going to write Lindlar PD, Lindlar palladium. We use that poison catalyst. It slows down our reaction, and our product will just be the alkene. So if we substitute the Lindlar PD for our reaction here in the middle, instead of producing our butane here from our butene, we would produce our butene with that double bond still remaining in our product. The next reaction that we'll look at is hydrohalogenation. Again, of course, this is a reaction that occurs with alkenes as well. In this reaction, we're adding a hydrogen halide to our double or triple bond. As we'd expect, we end up with our hydrogen getting added on one side and our halogen getting added on the other side. So we can get a alkenyl halide produced here from our reaction, where we still have our alkene double bond and our halogen. However, since our alkene, of course, also reacts with hydrogen halides, depending on how much of our hydrogen halide we have, right? If we have excess hydrogen halide, we'll actually continue to react, and we'll react again to produce a dihalide. So you might notice this is essentially the reverse of the double elimination that we can use to form alkynes. We're essentially just adding on those halogens that we would have eliminated in that double elimination reaction. So if we have an alkyne such as our 4-methylpentine shown here, and we add on our hydrogen halide, we'll use hydrogen bromide in this case. So we add on our bromine. Notice our bromine is adding on at the more substitute position, right? We're still following Markovnikov's rule here. And again, if we have excess of our hydrogen halide, we would add that on again, doing one step further than our alkene addition reaction. We again follow Markovnikov's rule, producing our geminal dihalide. Now, while this reaction looks very similar to our alkene hydrohalogenation reaction, there are actually some slight differences in the mechanism. So one of the interesting things that we see if we look at this with kinetic studies is that the rate actually depends on the alkene, and it has a square dependency on our hydrogen halide. Now when you see a square dependency like this in your rate law, that suggests that our hydrogen halide is actually playing more than one role in our reaction mechanism. So this actually suggests a concerted mechanism where we're going to be reacting with 2 units of our hydrogen halide at the same time. So we tack as a nucleophile on our hydrogen, just in the same way as we would in our alkene hydrohalogenation reaction, while at the same time we also attack with our bromine as a nucleophile. So this is going to be attacking at the same time in a concerted mechanism, and the 2 units of bromine, hydrogen bromide, that are involved here is what gives us that squared relation in our rate law. So they both attack at the same time. We don't actually have a true carbocation intermediate, but we still end up following Markovnikov's rule because, of course, our transition state will have partial positive charges that will favor the more substituted position. Our next reaction is hydration. Hydration, of course, involves addition of water to our alkene or alkyne. Remember, we always require some kind of acid catalyst here. So I'm just using H+ to represent any strong acid that's going to be donating those H+ ions. As we know, the H+ gets donated to our alkene or alkyne. It's using its excess electrons to take that H+, and then we're adding on our water to create an alcohol. So if we repeat that same reaction with our alkyne, so we end up with our OH and our hydrogen attached on either side of our alkyne triple bond. Now you might expect, as with our other reactions, that we would just react again with the second unit of water and produce a dialcohol product, a diol, we would refer to this as. However, before we get to that potential diol product, we actually have something interesting that happens here with our intermediate. So we call this a enol. Ene, of course, referring to our alkene double bond, and the OL referring to our alcohol. So we're not going to follow the normal path to our diol. Instead, this enol is going to rearrange into another isomer. So this will rearrange into a carbonyl, where we have a carbon-oxygen double bond, and our carbon takes an extra hydrogen. So notice this is just an isomer of our enol up here, right? We just took our double bond and moved it over, and took our hydrogen and moved it over there, right? So the same exact atoms, we just rearranged it to form what we call this carbonyl, which is our carbon-oxygen double bond, or this is also called a ketone. So this is actually a spontaneous isomerization, right? We're changing from one isomer into the other. This occurs relatively quickly. It's highly favorable to form our ketone product instead of our enol, right? So our ketone is much more stable compared to that enol. This sort of spontaneous isomerization we refer to as Tautomerization. So it's our isomer rearranging into a new isomer spontaneously without us even needing to add an additional catalyst. So our overall reaction then will actually go from our alkyne to this ketone here instead, with our carbon double bonded to oxygen. Our tautomerization process actually gets sped up by the same acid catalyst that we use for our initial hydration. So we have our acid that's providing H+ ions, and our alkene is going to use its nucleophilic nature, those extra electrons here, to attack and be protonated by our H+. At the same time, our oxygen, of course, also has excess electrons, and so it's going to share those with our carbon so that we don't have a carbon without the full octet. This results in our double bond forming between our carbon and our oxygen. We end up with a positive formal charge on our oxygen since it's now sharing its electrons with our carbon. And our other carbon over here picked up that extra hydrogen as it attacked our H+ ion. From here we can bring in our water, which again we used in our hydration. And we can deprotonate that hydrogen and form our ketone. So the tautomerization mechanism is very simple. It's just using the same acid catalyst and water that we already have present. You can also do a tautomerization with base as well, but of course in our hydration reaction we're not going to have any base present since we have that strong acid here. Let's look now at the specific example of my 1-hexyne reacting in this hydration mechanism. So we're going to use our strong acid. So here we have sulfuric acid. That's one of the strong acids that we commonly use in organic chemistry. We're actually commonly going to use a mercury-based catalyst as well here to help speed up our reaction. This is commonly used in our alkyne hydration reactions. Our product, we are going to see that ketone product. We don't see our enol intermediate because it immediately tautomerizes and rearranges to get that product there. So we're going to have our 6 carbons still. So we have our 6 carbons, and our double bond to the oxygen ends up at the more substitute position following Markovnikov's rule from our initial alkyne. So again, we need to follow that Markovnikov's rule, as always with these addition reactions, with the exception of those rare anti-Markovnikov reactions. Our next reaction involves halogenation with our diatomic halogen. So in this case, again, with our alkene, remember that we added that halogen onto either side of our bond, and we did this in an anti-fashion, which interestingly is continued for our alkyne. So we get them adding on in an anti-fashion to create a trans isomer, right, where our halogens are on opposite sides of our new double bond that forms. This trans product suggests that this might be an anti-addition where they're getting added on opposite sides. So that implies that we might actually have a halenium ion intermediate, kind of like the halonium ion intermediate that we had for our halogenation of alkenes, where we have some kind of our single halogen adding on and creating some positively charged cyclic structure perhaps, and then our second halogen attacking on the opposite side to create our anti-addition product. Now it's not known for sure if this selenium ion intermediate actually forms, but it does explain this sort of anti-addition that results in our trans product. Now as with our hydrohalogenation, our double bond of course is still reactive to that halogen. So depending on if we have a small amount of halogen or a large amount of halogen, we can actually react a second time and create a tetrahalide where we add on a second halogen onto either side of our double bond. Right? So both of these products are possible depending on how much of our halogen we have. Again, let's look at a specific example using our alkyne here. So we'll react it with diatomic bromine. Our bromine will add on to that double bond. We get our initial product, our trans isomer with our bromines added on either side. And then if we add more bromine, we can get that tetrahaloalkene product with our 4 bromines added on to our alkane chain. Again, this will be controlled just by how much of our bromine we add relative to our alkyne. If we have a 1-to-1 ratio, we'll just end up with this alkene product. If we add a 2-to-1 ratio of bromine to our alkyne, then we'll get mostly our tetraalkyl product. It is important to note here that while I'm using X2, this will actually only be useful with chlorine and bromine. We don't see this reaction occurring with fluorine or iodide or other halogens. So X2 is just referring to chlorine or bromine in this case. The final reaction that we'll look at for our alkyne is the ozonolysis reaction. Again, ozonolysis is something we saw with alkenes, where the ozonolysis caused our double bond in that case to break apart, resulting in new carbonyl-based compounds. Our ozonolysis with alkynes are going to be very similar. We're again going to be splitting this bond, but our products will look a little bit different, right? So we're going to again take a step beyond our normal products into something that's new. So our ozonolysis reaction here is going to require, of course, ozone, as before. It wouldn't be ozonolysis if you didn't have ozone. But we'll have again a second step where we're breaking apart an ozonide-based intermediate. But in this case, we only need water to break our intermediate. So our alkyne is actually a little bit more reactive than our alkene. And so we don't need that reducing agent that we used before. So this is going to break apart our alkyne. So we're going to have our single carbons on either side with, of course, whatever carbon-based chains might have been attached to those carbons. And instead of just adding the 2 bonds to oxygen, we now need an additional bond to take the place of our 3rd bond in our triple bond. So this is actually going to be a 3rd bond to oxygen, and we'll end up with these OH groups attached to each of our carbons. So our carbons start with 3 bonds to the other carbon. This gets split, and we add in 3 bonds to oxygen to make what we call carboxylic acid functional groups. So we go from our alkyne to our carboxylic acid, and we also are going from a larger molecule into 2 smaller molecules. Again, we can look at a specific example to illustrate the products that would form. So here we have our alkyne here, so this is another isomer of our pentyne. We're going to be splitting it right down the middle of our triple bond with our ozone and forming our carboxylic acids. So our structure on the one side will look just like our alkyne, but it'll stop right here at this carbon, and we'll add on our 3 bonds to oxygens. On the other side, we have just our single carbon. So this single carbon will actually end up with 4 bonds to oxygens, making carbonic acid. This is only the case when we have just a single carbon that's split off in our ozonolysis reaction. So this will occur whenever we have terminal alkynes. If we have internal alkynes, we'll just end up with 2 different carboxylic acids. In this video, we've looked at a wide range of different alkyne addition reactions. Right? We have our hydrogenation, our hydrohalogenation, hydration, halogenation, and of course our ozonolysis reaction, which is kind of a little bit different from our typical addition reaction.